Hello, and welcome to our presentation of the paper, Combined Convolutional with Recurrent Networks for Text Classification. The outline of this presentation is as follows. We'll first go over the paper's goals and key contributions. Then we will review some results the paper found, and we will define and explain the proposed convolutional recurrent neural network architecture. In addition to the architecture, we will also interpret the learned weights of the network. At the end, we will present some critiques of the paper and finish with a short recap of the presentation. The goal of this paper is text classification. Text classification is the task of assigning a set of predefined categories to natural language texts. An example involving text classification would be, given a set of news articles, is it possible to classify the genre or subject of each article? Genres include, but are not limited to, technology, sports, or entertainment. In practice, convolutional neural networks can be used to classify texts based on the semantics of the sentence. Recurrent neural networks can be used to classify texts based on the context of the word in relation to the sentence. This paper suggests a new method involving both these networks. This paper suggests an enhanced method of text classification by proposing a new way of combining convolutional and recurrent neural networks involving the addition of a neural tensor layer. The proposed method maintains each network's respective strengths that are normally lost in previous combination methods such as streamlining the two networks. The new suggested architecture is called Convolutional Recurrent Neural Network, which utilizes both a convolutional neural network and a recurrent neural network that run in parallel on the same input sentence. The convolutional neural network produces a 2D matrix that shows the importance of each word based on local and position invariant features. The bidirectional recurrent neural network produces a matrix that learns each word's contextual representation, or in other words, its importance in relation to the rest of the sentence. A neural tensor layer is introduced on top of the recurrent neural network to obtain the fusion of a bidirectional contextual information surrounding a particular word. That is, the importance of a word when a sentence is read right to left and when it's read left to right. The architecture combines these two matrix representations to classify the text, as well as offer the importance information of each word for the prediction, which can help with the interpretation of the results.
In this section, we will review the results presented in the paper. In order to evaluate the performance of the CNN model and compare it to previous efforts, a benchmark was created from 6 publicly available datasets. For sentiment analysis, the movie reviews and Yelp datasets were used. Then the Ages News, 20 News Groups, and Sogo News datasets were used for the problem of news categorization. Finally, the Yahoo Answers dataset was used for the problem of topic classification. In this chart, we see the classification accuracy of each model on each of the 6 benchmark datasets. The performance of each model was scaled relative to the CRNN model for easier comparison purposes. We can see that the CRNN model, on average, was the best performing model, and in fact the only model which performed better than the CRNN model was the self-attentive LSTM, and that was only on 2 of the 6 datasets. Here we will give a brief overview of the CRNN model architecture. Here we have the RNN pipeline as well as the neural tensor layer, and then parallel to it is the CNN pipeline. Both of these are combined at the end to find our classification results. In this section, we'll give an overview of the RNN pipeline, which is highlighted in color on the diagram on the right.
The goal of the RNN pipeline is to capture for each word in a text the contextual information surrounding the word. This will be done using a bidirectional RNN. The second component is utilizing a neural tensor layer to compute the word's contextual representation by combining the results of the RNN. Both of these concepts will be explained further in the following slides. Now let's take a closer look at how an RNN actually operates. It's very similar to a feed-forward neural network as we learned in class, but the fundamental difference lies in the use of hidden states. You can see in the first network, the one to the left, that the output of the hidden layer is looped back into the hidden layer. This can be done a numerous amount of times, and this is what we referred to as the hidden state. This is ideal for processing sequential data such as text and text required for NLP tasks in particular. So now if we take a closer look at the diagram towards the left, consider the input xt. The network uses the information from the previous input encoded within the hidden state ht-1 to forward propagate. Note that U, Z, and W are just weight matrices that our model will need to learn. So at this current time step, we see that YT is the output and HT is the newly computed hidden state that is pushed towards the next forward propagation of the input xt plus 1. In our case, each xi represents a word in a text x. So now consider an example. Consider the sentence, what time is it? If we train a network that does not keep track of the information from the previous word, when we do the forward propagation to finally classify the text, it will only use the last word. Training an RNN and using a feed-forward layer on the last output of the text would have information from all of the words that came before the word it. So the model will be able to keep track of what time is it, so they know that it'll be able to learn that we're asking for the time. So for RNN, we'll be using a variant called graded recurrent units, or GRU, which helps to address the problem of the vanishing gradient. The problem implies that the network struggles to memorize words that came earlier in the sequence and can only keep track of words that came very recently in the sequence. To combat this, a GRU helps to control the flow of information. This allows the network to decide how much information from past words is important to the current word. And if it decides that a word that came really early in the sequence is not important anymore, then the network will forget it. So the main mechanism of a GRU is update and reset gates. So the left diagram shows how each hidden state at time t would be computed in a traditional RNN. Each of xt and the previous hidden state, ht minus 1, would be multiplied by the weight matrices, which are implied right over here, and they would be sent through a sigmoid function, an element-wise sigmoid function, and then multiplied again by weight matrices to compute yt and the next hidden state, ht. The right shows how a GRU would behave with the same outputs. So let's take a closer look at a GRU and how it differs from a traditional RNN. So notice first off that the inputs of the GRU are the same as a traditional RNN. So we still have xt, the current input, and the previous hidden state, ht minus 1. Now before we do any other computations, let's define a few matrices and vectors. So you have xt, the input, an n-dimensional vector, the previous hidden state, which is an m-dimensional vector, 3 weight matrices, wz, wr, wh, which are all m by d matrices, and another 3 weight matrices u, uz, ur, uh, which are m by m matrices. Note that all of the functions here are element-wise. Okay, so the first step is to compute the update gate zt. So this will tell the model how much past information needs to be passed on. This is done by computing xt times a weight matrix plus ut times plus uz times the previous hidden state ht minus 1. And then you'll sum that, shown right over here, to get, and then activate it using a sigmoid function to get zt. Now we compute the reset gate, which tells the model how much past information needs to be reset or essentially forgotten. So this is not done in a very similar fashion. We multiply xt by a weight matrix, multiply the previous hidden state by a weight matrix, sum that, and use the activation function sigmoid to get rt. So the only way these two methods differ is just by the weight matrices we have over here. Cool. So the next step is to compute new memory tilde ht. This is essentially the relevant past and current information that the model has decided to keep, utilizing the reset gate rt that we had just computed before. So here again we have xt multiplied by a weight matrix over here, and we take the hidden state again from before and multiply that by rt, so element-wise multiplication by rt, and then we sum the results of those right over here, which is given by this over here, and then we activate that using the tanh function to get h tilde t. Now the last step is to use zt to influence how much memory is kept and forgotten. So the first computation we'll do is zt times the previous hidden state, so that can be shown right over here. And this influences the weights of the previous hidden state that will be retained. And then we do 1 minus zt over here times the times h tilde ht that we had just computed. And this incorporates the new memory components that our reset gate has decided to retain. And we sum that to get our new hidden state, and we can also compute a new output yt from here.
A word's contextual representation is argued to be more precise when the information that is processed from both directions are fused. In order to capture the context information of each word, a bidirectional GRU is used to process text X. Hidden states h forward and h backwards contain contextual information around the ith word in forward and backward directions respectively. Conventionally, these two vectors are concatenated and fed into a fully connected network. But these two vectors hold no influence over each other, which causes the compositional meaning of the context to be missing from the resulting vector. It is argued in this paper that the word's contextual representation is more precise when the context information from different directions is fused using a neural tensor layer. A neural tensor layer is applied via a neural tensor matrix. It permits greater interactions among each element of hidden states and is argued to aggregate meanings from forward and backward hidden states more accurately than simply concatenating them. Through each neural tensor layer, the resulting vector hi hat can be viewed as a different type of intersection between h forward and h backwards that retains each of the respective contextual meanings. After getting h hat, we concatenate h forward, h backwards, and h hat to obtain vector h bidirectional, which summarizes the context information centered around word t. It's the meaning of the word in relation to the other words in the sentence. For the sake of convenience, we stack all h bidirectionals for each word into matrix H, which has shape n by 3m, since there are n words and m hidden states. We note that all h vectors, h forward, h backwards, and h bidirectional, all have the same size m.
Now we will discuss the convolutional neural network pipeline, which is shown here in color as the bottom half of this diagram. Let's start with the CNN pipeline interface. The goal of the CNN pipeline is to learn the relative importance of n words in an input sequence based on z different aspects. The pipeline's input are word vectors from word to vec, and the pipeline's output is the attention matrix A with relative word importance. Everything else in this diagram is internal implementation detail that we will now introduce step by step. So starting with the basics, we take a single word and we feed it to our word to vec algorithm, which returns a fixed length word vector shown in green here. We repeat this for all n of our words to get n word vectors. We then concatenate the word vectors into a matrix X, which is n by d, where n is the number of words and d is the fixed length word vector size from word to vec. We then take a filter, which we represent with matrix Wj as the pink rectangle in the top left, and then convolve this pink filter over our word matrix X, essentially sliding this pink rectangle from the top of matrix X to the bottom. This is similar to how filters are convolved with images in traditional CNN models, except the values being convolved are features from word to vec rather than image pixels. Each convolution for a filter Wj gives us the feature Cji. We repeat this convolution n times for the same filter Wj, which gives us vector Cj, which is a k-gram vector that the filter extracted. We repeat this process again, but for L filters of different sizes to extract L number of k-grams of different sizes, which gives us matrix C, which is the concatenation of all the k-grams C1 to Cn. Lastly, your intuition may tell you that some k-grams will be more meaningful than others depending on the task and the aspect. This intuition is correct. And so we introduce the matrix W, which learns to weigh important k-grams more heavily than less important k-grams. This reweighting gives rise to the attention matrix A, which stores the relative importance of words based on z aspects, where z is a hyperparameter. Notice that in green, the word matrix X, and in red, the attendant matrix A, each row vector of both matrices represents the same word, but with different fixed lengths, because X was learned through word to vec, and A was learned by different aspects.
So now that we've seen how a CNN and an RNN will operate in this context, it's time to combine the two models as suggested by this paper to achieve a better performing model. So we do this by combining the two matrices A from the CNN output and H outputted by the RNN model to compute S. So this is just done simply by taking the transpose of A and multiplying by H, which will result in a matrix of size Z by 3m. And then we concatenate all the rows. So essentially we'll end up with a vector that is 3z by m. The final step is to pass the concatenated S through a final fully connected softmax layer to determine the probabilities for each class. Now during training we have certain considerations that we'll make. So our loss function will be cross entropy loss, which is the negative sum of products between yi, which is the true class probability, and hat yi, the predicted class probability. And this is summed over all classes I. And in order to prevent overfitting, we'll do two things. So the first will be performing dropout on columns in matrix C, which is from the CNN pipeline, during the training process by zeroing out the selected columns, and also utilizing L2 regularization on all parameters. We'll also be using stochastic gradient descent with a learning rate of 0.001.
Now that we've gone over the CNN pipeline, we can now look into how to interpret some of the learned weights in the cRNN architecture. In particular, we'll be looking at attention matrix A in the red here in this diagram, and it is the last component exclusive to the CNN pipeline. Digging in deeper, matrix A essentially stores the relative importance of every word in the input sequence for every aspect chosen. Naturally, this means that A is a n by z matrix because n is the number of words in the input sequence and z is the number of aspects being considered in the classification task. Furthermore, for a specific aspect, words with higher attention values are more important relative to other words in the same input sequence. For a specific word, aspects with higher attention values make the specific word more important compared to other aspects. For example, in this paper, a sentence is sampled from the movie reviews dataset, and the transpose of attention matrix A is visualized. Each word represents an element in matrix A. The intensity of red represents the magnitude of an attention value in A, and each sentence is the relative importance of each word for a specific context. In the first row, the words are weighted in terms of positive aspect. In the last row, the words are weighted in terms of a negative aspect. And in the middle row, the words are weighted in terms of both a positive and negative aspect. Notice how the relative importance of words is a function of the aspect.
In this section, we'll present our criticisms of the paper. Firstly, we found that in some explanations of the model, there was a so-called overloaded notation where the same notation was used for different components of the model, and therefore it was unclear to tell which part of the model it was referring to, since they had the same notation. And then in the results sections, there was some poor explanations of the interpretability of their model, where they presented the results and did not really go deeper into the meaning behind their results and the better interpretability of their model. And then finally, their performance comparison to other models, which was omitted in this presentation for sake of brevity. The other models were compared on the same datasets, but the datasets were not necessarily prepared in the same way or even using the same data because they were only subsets of the entire dataset, and therefore they claimed better performance than other models, even though it wasn't really the same classification problem because the data would be possibly different. So we get a sort of apples to oranges comparison there, which was presented as a better result with the CNN model.
In conclusion, this paper suggests a new method to combine convolutional and recurrent neural networks for the purpose of text classification. The two neural networks are combined via matrix multiplication, and each network's resulting matrix is built and fine-tuned using methods to maximize the learned material for each matrix. The convolutional network produces a matrix that contains the relative importance of words in relation to the sentence, whereas the recurrent neural network produces a matrix that contains the contextual information for each word in relation to the sentence. The proposed architecture still has a few improvements that can be made, but overall appears to produce good results. Thank you for listening to our presentation. We hope you have a good day.